Hi there, I'm Hans H. Stein, and I'm a professor at the University of Illinois. And I'd like to talk to you today about corn and corn co-products fed to swine. First, I'd like to talk a little bit about the composition of corn. And a typical corn grain contains about 11.3% water, 8.3% crude protein, 3.7% fat, 1.3% ash, and 62.6% starch. And then on top of that, we also have some fibers, and that is divided into NDF at about 9.1%, ADF at 2.9%, and then we have lignin at about 0.3%. We feed a lot of corn grain to our pigs, and when we feed corn grain, we get exactly the composition that is showing here. However, corn is also used for many other purposes, and as the industry utilizes corn, there's usually a part or a fraction of the corn grain that cannot be utilized for the primary purposes, and those fractions are usually available for the feed industry and therefore also for the swine feed industry. What happens on most occasions is that industrial use of corn grain results in removal of the starch. There are a few exceptions to that, but for most purposes, starch is removed, and then we end up with the other components in the corn grain except for the starch. And if that happens, then obviously all the other components will be concentrated because, as appears here, starch is almost 2/3 of the corn grain, and therefore if you remove that starch, then you end up with a much greater concentration of all the other components. So in most of the corn co-products we work with, we have greater concentrations of crude protein and fat and fiber than we have in corn grain. Sometimes some of those other nutrients are also removed, and therefore we can have wide variety of concentrations of nutrients in the corn co-products that are available to us. If we look at the concentration of metabolizable energy in corn grain, then we have here values from 9 different experiments that have been conducted here at the University of Illinois over the last few years. And you'll see here that the concentration of metabolizable energy in these 9 different sources of corn grain on average has been 3,846 kilocalories per kilogram dry matter. And you'll also notice that the variation in the energy concentration in corn has not been very big. It's about 2 percentage units, and there's less variation in the metabolizable energy in corn than there are in most of our other ingredients. We can also compare the digestible and metabolizable energy of corn to that published from other sources. You'll see here that the 9 sources that we have worked with at the University of Illinois on average contain 3,950 kilocalories of digestible energy and 3,846 kilocalories of metabolizable energy. And if you divide those two numbers, then you'll get an ME to DE ratio of 97%. Those values are very close to the values that have been published by NRC in 1998 at 3,961 kilocalories per kilogram dry matter and 3,843 kilocalories per kilogram dry matter, respectively. And NRC also reports an ME to DE ratio of 97%. And if we go to Europe and look at published values there, then we have INRA values that were published in 2004, and the average DE in the INRA tables are 3,927, and the ME is 3,844, and it's clear from this table that the European values are also very close to the values that have been determined here at the University of Illinois and also that have been published by NRC. Now, if we look at the corn co-products, we can roughly divide them into 2 separate groups. One group of corn co-products are the co-products that are produced by the ethanol industry, and the other group consists of all other co-products. The co-products from the ethanol industry includes distillers dried grains with solubles, also called DDGS. We have high-protein distillers dried grains, or HPDDG. We have corn germ, and we also now have de-oiled DDGS and low-oil DDGS. So we have at least 5 different co-products produced by the ethanol industry. The co-products that are available to us from other industries include corn gluten meal and corn gluten feed, and both of those products are from the wet milling industry. We also have corn germ meal, which may be produced by either the wet milling or the dry milling industry, and we have hominy feed, which is a co-product from the corn grits industry. If we look at the composition of the co-products from the ethanol industry, then we have here DDGS, DDG, high protein DDG, and corn germ. And I've also included corn grain in this table here. And we will see that the concentration of crude protein is greater in all the corn co-products compared with corn. It is about 27.5% in DDGS, 28.8% in DDG, and 41.1% in high protein DDG. And then we have corn germ with only 14%. Fat is also greater in DDGS than in corn, and it's much greater in corn germ than in corn because the corn germ contains the majority of the fat that is present in the corn grain. However, HP DDG has a relatively low concentration of fat. As we saw before, the corn grain contains approximately 65% starch, but most of that starch is removed when we come to the corn co-products. So DDGS contains only 7% starch, DDG 3.83% starch, HP DDG 11.2% starch, and corn germ about 23.6% starch. The fiber can be expressed as NDF, and the corn grain contains less NDF than DDGS, HP DDG, and corn germ, and also less than DDG. So we will see that the fiber concentration is much greater in these co-products than it is in corn. And if we look at lysine, we'll see that all the corn co-products contains more lysine than corn, and it varies from 0.78% in DDGS to 1.23% in HP DDG. If we look at the metabolizable energy in the corn co-products, you'll see we have corn here at about 3,800 kcal per kilogram dry matter, as we showed before. DDGS is very similar to corn in terms of ME concentration, but high protein DDG contains more ME than does corn or DDGS. On the other hand, corn germ contains about the same as corn and DDGS, but if we take the oil out of DDGS and produce a de-oiled DDGS, then we will end up with a product that contains much less energy than the original product that we had. And we can see here in the green bar that the concentration of energy is much lower than it is in any of the other co-products. So the conclusion here is that corn germ and DDGS contain about the same amount of energy as corn. High protein DDG contains a little bit more energy than corn, but de-oiled DDGS contains much less energy than corn. We also have fat or lipids in all our corn co-products. However, the digestibility of that fat is different among different products. And we have some data here from extracted corn oil, from corn, from DDGS, from corn germ, from HP DDG, and also from soybeans. And it appears from this slide that the true ileal digestibility of lipids in these different sources varies quite dramatically. Extracted corn oil is very digestible, and the pig will absorb about 95% of the extracted corn oil if we add that to the diet. However, if we don't extract the corn oil and leave it in the corn, the digestibility is much less and only slightly above 50%. So there's a big increase in digestibility of corn oil if we extract that corn oil out of the corn grain. We can also see that the digestibility of lipids in DDGS and in corn germ is about the same as it is in corn. So that is also much less than in extracted corn oil. But when we come to HP DDG, we do see a slight increase in digestibility. But as we saw before, there's not a lot of oil in HP DDG, but whatever is there is relatively well digested. Full-fat soybeans also have a relatively high digestibility of lipids at about 85%. So the conclusion from this slide is that although lipids contain quite a bit of energy, there are relatively big variations among different corn co-products in the digestibility of these lipids. As we saw before, we have quite a bit of fiber in DDGS and in other corn co-products. And the fiber can be divided into insoluble dietary fiber and into soluble dietary fiber. And we have here the insoluble dietary fiber in the red bar and the soluble dietary fiber in the yellow bar, and the total dietary fiber, which is the sum of the insoluble and the soluble dietary fibers, in the blue bar. And when we look at the disappearance of fiber in the total tract of a pig, then we can see that the insoluble dietary fibers disappear by only approximately 40%. And that means about 40% of these fibers in DDGS are fermented in the intestinal tract of a pig. So the other 60% of the insoluble dietary fibers, they will just pass through the pig and be excreted in the feces. However, when we look at soluble dietary fibers, we can see that they are much more fermentable, so the disappearance is greater than 90% in the soluble dietary fibers. However, the concentration of soluble dietary fiber in DDGS is relatively low, so although the pig seems to be able to ferment the soluble dietary fiber very well, the influence on the overall digestibility or disappearance of fiber in DDGS is not that great, so the disappearance of total dietary fiber in DDGS is only about 50%. When we come to the amino acids, we can see that the digestibility of most amino acids in the corn co-products is approximately the same as it is in corn. The exception here is corn germ, where the digestibility is less than in corn grain. But for most of the other co-products, the digestibility of amino acids is similar to that in corn. However, the exception to that is lysine, which has a lower digestibility in DDGS than in corn, and the reason for that is primarily that there is some heat damage going on in DDGS when the ethanol industry is drying the product after fermentation. But with that exception, most other amino acids have the same digestibility in the corn co-products compared with corn. Over the last 5 to 7 years, there have been numerous experiments conducted to evaluate inclusion rates of DDGS in diets fed to sows and growing finishing pigs. And based on all these experiments, we can recommend inclusion rates of DDGS in diets for the different categories of pigs. And based on that, we recommend about 50% inclusion rate in diets for gestating sows, 30% in diets for lactating sows. We don't recommend usage of DDGS in nursery diets during the first 2 weeks post-weaning, but after that, we can use up to 30% DDGS in the diets. We can also use 30% in the growing finishing diets, but during the last 3 to 4 weeks before harvest, we recommend that the inclusion rate of DDGS is reduced to about 20% to prevent development of soft bellies and soft fat depots in the pigs. However, there are some systems, in particular in the Midwest, where usage of DDGS is much greater than what it has been recommended, and we see maximum inclusion rates going up to 40 to 45% both for sows and for growing finishing pigs. And many systems report excellent productivity based on these diets. However, the research to verify that these greater inclusion rates can be used has not been reported at this time. We also have recommendations for high protein DDG and corn germ, but fewer experiments have been conducted with these co-products compared with DDGS. However, based on the reported literature, we can recommend that high protein DDG may replace all the soybean meal in diets fed to growing finishing pigs, and corn germ can be included by at least 30% in diets fed to growing finishing pigs. In weaning pig diets, we can probably include up to 20% of each of these ingredients. However, there still is a lack of published research in this area. For sows, we also recommend up to 30% of both HPDDG and corn germ, in diets fed in lactation and in gestation. Now, that was a little bit about the co-products from the ethanol industry. However, as mentioned in the beginning, we also have other co-products available to us. Some of the other co-products include corn gluten meal, corn gluten feed, corn germ meal, and hominy feed. The blue bars on this slide shows the crude protein concentration in these co-products. The red bar shows the concentrations of acid hydrolyzed ether extract or fat. The orange bars shows the concentration of fiber or NDF, and the green bars shows the concentration of starch. And we will see that although all four co-products here, co-products of corn, they vary dramatically in the concentration of the different nutrients. Corn gluten meal contains quite a bit of protein and very little fat, medium concentration of fiber, and a low concentration of starch. Corn gluten feed has a much lower concentration of protein, a very low concentration of fat, but a very high concentration of fiber and does not contain any starch. Corn germ meal also has a relatively low concentration of protein and fat, but a high concentration of fiber and also contains a little bit of starch. And hominy feed has a low concentration of protein, contains more fat than the other ingredients, low concentration of fiber, and contains quite a bit of starch. So of all of these co-products, hominy feed is the only product that contains quite a bit of starch, whereas the other products are very low in starch. The amino acid digestibility also varies among these co-products. The digestibility of lysine is shown here in the blue bars, methionine in the red bars, threonine in the orange bars, and tryptophan in the green bars. And we will see that hominy feed has a lower digestibility of lysine compared with corn, whereas corn gluten meal has a greater digestibility of lysine. The same is true for methionine, where hominy feed and also corn germ meal and corn gluten feed have a reduced digestibility compared with corn, whereas corn gluten meal has a greater digestibility than in corn. When we go to threonine, we see the same thing with hominy feed having the least digestibility and corn germ meal and corn gluten feed having a digestibility that is approximately the same as in corn, and corn gluten meal having a greater digestibility. And finally, when we go to tryptophan, you'll see that hominy feed, corn germ meal, and corn gluten feed have about the same digestibility as corn, whereas the digestibility in corn gluten meal is a little bit greater than in corn. So what we can see here is that although all of these products are corn co-products, the digestibility of amino acids among these products is not the same. We also know that the quality of the protein varies among different feed ingredients. And here we can see the concentration of crude protein in soybean meal, corn gluten meal, and DDGS. And we can see that corn gluten meal contains more protein and DDGS less protein than soybean meal. However, when we look at the concentration of lysine and tryptophan, we can see the concentration is much less in corn gluten meal and also in DDGS compared with soybean meal. And that is easily illustrated if we calculate the concentration of lysine and tryptophan as a percentage of crude protein in each of these ingredients. And here we can see that soybean meal has a concentration of lysine in crude protein of about 6.35% and tryptophan of 1.37%, and these values are much greater than in the two corn co-products. The reason is that corn protein has a reduced concentration of lysine and tryptophan compared with almost all other protein sources and also compared with the requirement of the pigs. So every time we use a corn co-product, we have a low concentration of lysine and tryptophan in the diets, and we need to find a way of compensating that primarily by use of crystalline sources of lysine or crystalline sources of tryptophan to compensate for this low concentration in corn co-products. There are not many data on the concentration of energy in corn co-products, but some preliminary data from the University of Illinois for the concentration of digestible energy in corn co-products are illustrated in this slide. And we can see here that corn gluten meal contains more energy than corn. On the other hand, corn gluten feed and corn germ meal contain less digestible energy than corn, and hominy feed contains almost the same amount of digestible energy as corn. So if we include hominy feed or corn gluten meal in the diets fed to pigs, then we will not see a reduction in the diet energy concentration. However, if corn gluten feed and corn germ meal are used, then we may see a reduction in diet energy concentrations, and we may have to compensate that by adding fat or other high energy feed ingredients to the diets. When we look at the digestibility of phosphorus in corn and corn co-products, we have here data for corn, DDGS, high protein DDG, and corn germ. And we have data both without phytase and with the inclusion of 500 units of microbial phytase. You'll see here that the digestibility of phosphorus in corn and corn germ is relatively low if we have no phytase in the diets. However, when we look at DDGS and high protein DDG, the digestibility of phosphorus is much greater than in corn and in corn germ. And we believe that the reason for this increased digestibility is that DDGS and high protein DDG are products that have been soaked and steeped and gone through a fermentation process, and therefore some of the phytate molecules have been broken, and therefore more phosphorus is available for absorption. However, if we add microbial phytase to corn or corn germ, we can increase the digestibility quite dramatically and get up to almost 60% digestibility of phosphorus. In contrast, if we add phytase to DDGS, we don't see a significant increase in digestibility, probably because the digestibility already was quite high in DDGS, and therefore microbial phytase does not result in a further increase in digestibility. And the same is true for HPDDG, where we see a very small increase in digestibility when we use phytase, and not nearly to the same extent as we saw in corn. So the conclusion here is that DDGS and high protein DDG, they have a high digestibility of phosphorus, whereas the unfermented products, which are corn and corn germ, they have a much lower digestibility, but the digestibility in corn and corn germ may be improved if we add microbial phytase to the diets. If we look at the standardized total tract digestibility of phosphorus in other corn co-products, we'll see here that the digestibility of phosphorus in corn gluten meal, corn gluten feed, and corn germ meal are all greater than in corn if we don't use any phytase. However, the digestibility of phosphorus in hominy feed is about the same as in corn. If we use phytase, then we can increase the digestibility of phosphorus in corn, as we've seen before, to about 60%, and we see almost the same increase in hominy feed. Corn germ meal will also have an increased digestibility of phosphorus if we use phytase, and the same is true for corn gluten meal. However, corn gluten feed does not see an increase in digestibility of phosphorus if we add phytase. But corn gluten feed had the greatest digestibility without phytase, so the reason we don't see an improvement when we add phytase to the diets is likely that there's no room for further improvement of the phosphorus digestibility in corn gluten feed. So in conclusion, we have seen that DDGS may be included in diets fed to pigs at relatively high concentrations, and by using DDGS at relatively high concentrations, most producers can save on diet formulations. However, it is important that we know the lysine digestibility in DDGS so we can predict the digestibility in the diet, and therefore can formulate a diet that contains enough lysine to meet the requirement of the pigs. We've seen that HPDDG may replace all the soybean meal in growing finishing diets and be included by at least 20% in weaning pig diets and 30% in diets fed to sows. Corn germ may also be included by about 20% in nursery diets and 30% in all other diets. And we've seen that the phosphorus digestibility in DDGS and HPDDG is close to 70%, whereas it is less in corn germ and in corn. We do need more research to determine the inclusion rate that may be used for corn gluten meal, corn gluten feed, and corn germ meal and hominy feed if we include that in diets fed to pigs. We don't know exactly how much we can include in these diets, but it appears that all of these products have good energy values, have relatively good amino acid digestibility, and have excellent phosphorus digestibility. We also believe that it's possible to include 20 to 30% of corn gluten meal, corn gluten feed, and corn germ meal in diets fed to all groups of pigs, but we do need research to confirm this. And finally, we do believe that hominy feed may replace at least 50% of all the corn in diets fed to all categories of pigs. With that, I want to acknowledge my students and technicians who have helped conduct the research I've talked about here, and we do have more information about all our research projects at our website, which can be found at nutrition.ansi.illinois.edu. With that, I want to thank you for your attention, and I hope you will have good luck using corn co-products in diets fed to pigs.